Welcome to the Niels Bohr Institute cleanroom facilities. We are research infrastructure that supports condensed matter physics research, and we are specialized in nanofabrication, where you in the end can have electronics and photonic circuits that can manipulate single electrons and photons. Our chemical labs and process labs are designed to support this kind of research, and we are currently on our way into our cleanroom facilities. Let's go have a look. So this is one of our cleanroom labs. The air inside here is changed more than 60 times every hour. This is to ensure a very low number of particles in the air. Our devices are sensitive to particles, so we want to control the number of particles inside and reduce the amount as much as possible. In here we have fume hoods for chemical processing. In this video we will go through some of the basic processing that we do in electron lithography. And some of those processes involve chemical treatments and exposure using electron beams. In an E-beam lithography process, our starting point is a silicon wafer. We spin coat this wafer with a thin layer of polymer that is sensitive to an E-beam. Then, after exposing the polymer locally with this electron beam, we can develop the polymer and only remove the part that was exposed. After that, we can evaporate a thin layer of metal on the surface, which creates a contact to our semiconductor or our nanomaterial. So the first part of the electron beam lithography process is spin coating. The starting point is a blank piece of semiconductor, like this silicon wafer here. And what we need is to distribute a thin layer of polymer on the surface of this silicon wafer. To do so, we place it in a spin coater. We apply a vacuum to keep it tight. Then we disperse a small amount of this electron beam sensitive polymer, called a resist. Right now the resist is liquid, and once we spin it, it will distribute across the surface in a very, very thin layer, and afterwards we will bake it to harden the polymer. The starting point of nanofabrication is usually a semiconducting surface or nanomaterial, often in combination with a superconductor. We can grow nanomaterials locally here at the Institute in a system that is located in a process lab just inside here. There we will meet Magnus, who is doing a project there. Please follow.
This is an ultra-high vacuum chamber, which means that the pressure in here is similar to the pressure in outer space. And the reason that why we keep this low pressure is that we need to grow ultra-high quality crystals for use in quantum computers. The problem is that if we have a higher pressure, we'll get a lot of impurities in our crystal. And with a quantum computer, it's absolutely crucial that the crystal is as pure as possible, because any impurities will cause the system to be non-ideal and cause the quantum states to sort of decohere over time. And this is something that inhibits the function of the quantum computer. So that's why we need the ultra-high vacuum chamber for this process. Right now we have the sample inside the high vacuum growth chamber. But the process for getting the sample into the growth chamber is actually very long, and it starts over there. What we see here is the load log. So the first step is that we take our sample from one of these boxes right there and put it into the entry-exit chamber in there. Once it gets to the entry-exit chamber, it has to be heated to about 200 degrees for 4 hours in order to evaporate any water or similar material from the atmosphere before we can take it to the next chamber, which is the buffer chamber. Here we see the trolley with a lot of samples that we use to move the samples around inside the vacuum chamber. So once we're done moving it from the entry-exit chamber to the buffer chamber, we put it on the next heating station right here, where the sample gets heated to about 400 degrees for 2 hours to evaporate any excess impurities from being out in the atmosphere. And once that heating is done, we can transfer it all the way into the ultra-high vacuum chamber. I've now heated the electron gun, so I'm shooting electrons in from over here, and they hit the sample, which is in the middle of the vacuum chamber, and reflect off to hit this fluorescent screen right here. And what we see on this screen actually gives us some insight about what's going on the crystal surface.
My name is Zhe, and I'm a clean room staff in NBI. Now I'm responsible for this lab, Quantec, which has a Linux F125 tool for exposure. This tool has a super high acceleration voltage, which is 125 volt. That you can show the super high column from here, and it's used to transfer patterns onto resist on the chip, so we can do some folding procedure afterwards.
So after development, the sample is ready for a thin film evaporation of either ohmic contacts or superconducting contacts, and for this we use our thin film e-beam evaporator just inside here, where we will meet Oliver.
Hi, my name is Oliver. I'm a master's student here at the Niels Bohr Institute at the University of Copenhagen. I'm a master's student of physics, and more specifically, I work with quantum information and quantum computation. And now, to get this quantum computation to work, we need physical systems. And this physical system that we use is a microchip. And I work with spin qubits, meaning that I actually fabricate these microchips that have thin metal gates on them. And these metal gates are deposited using this machine. This is a depositioning machine, and this is what we use to put down a thin film of, be it gold, platinum, palladium, your choice. But this is what we use to actually put down this thin layer of gates that we use to actually realize these qubits in our microchips. Here you see the sample holder with a microchip attached with a piece of tape. Now the first thing we're going to do is we're going to put this into the machine, like so. Make sure it's properly attached. Close this lid and turn on the vacuum. Now this vacuum that we turned on is for the loading chamber. We load into the loading chamber. When this has come down to a vacuum, we can then open the hatch, put it into the main chamber, take it back out and close the hatch. So now the chip is in the main chamber. The main chamber is where it all happens. After the chip has been put into the main chamber, we can then choose the metal we want to deposit. Once we've chosen the metal we want to deposit, we turn on the power source, ramp up the electron beam, and what this electron beam does is it goes down, it hits the metal in the crucible, and lets the metal evaporate. So when this metal evaporates, it can actually travel up through the vacuum of the main chamber and hit our microchip, and thereby depositing a thin layer of whatever metal we've chosen. Now, we can keep an eye on how thick this layer is by using this menu here, and once we've reached our desired thickness, we turn off the e-beam, turn off the power source, close the shutter so nothing more gets deposited than what we've already seen is, and then we can do the reverse, take it out of the main chamber, put it back into the loading chamber, turn off the vacuum so that we can go in and grab our chip out, and then we're done.